Okay, thank you very much to Dr. Frost and Mr. Andrew Blackett for another fantastic PowerPoint presentation. So we're going to be looking at linear programming. As you know, we've already covered algorithms, graphs and networks, algorithms on graphs, route inspection, the traveling salesman. Now we're doing linear programming. This is completely different to everything we've done. Okay, we're going back to kind of old school problems. Basically, what we're going to be doing is solving simultaneous equations graphically to find an optimal solution. So that is what we're actually doing here, okay? So, it is an optimization technique, and we're going to be looking, when we look at our constraints, essentially we will be looking at them in the 3D plane. Okay, so our coordinates are going to be X, Y, and Z, or Z. Wait, is Z English?
I think Z is.
And Z is American. Okay, anyway, I'm going to call it Z. Okay, is everyone happy with that? So, I'm not going to tell you where it's going to be useful. You're going to see how useful it is once we start looking at the problems, okay? So, for the first part of this chapter, what we're going to do is we are going to look at what's called formulating the problem. Now, when we have exam questions, there's two types of exam questions. One is where they give you it and you have to formulate the problem and then solve it. The other one is where they've given you the problem and then you have to solve it. Okay? There's a few different types. A lot of the linear programming questions are about 14 marks, roughly. So as you can imagine, what's 14 out of 75? It's about a fifth, right? Roughly a fifth. Okay? So roughly a fifth of the marks are on a linear programming question. Okay, so let's make sure we get it. So, Mr. Blackett is thinking of taking a break from teaching decision maths and setting up a business, making and selling Mobius strips and Klein bottles hewn from solid gold. I have no idea what any of that means. JP would know. Perfect. He invests in a 3D CNC milling machine and sets about defining the constraints as a linear programming problem. So, okay, I'm just going to call this B for bottle. Each bottle takes 2 hours to mill and 3 hours to polish. Okay? Each strip takes 3 hours to mill and 1 hour to polish. The milling machine can run for 80 hours per week. Mr. Blackett can polish for 60 hours a week. He believes he can make £2,000 profit on every bottle and £1,000 profit on every strip. He wishes to maximise his profit. Okay, now this will always be the rule in any of these. Step one is always step one. Define the variables, okay? So let's X equal bottles and let Y equal strip. Everyone happy with that? You have to write this down or you will not get the mark. You have to define the variables, okay? It then says maximize. This is the objective, okay? We need to state the objective. So, because we're trying to maximize profit, we will write maximize P equals, now our profit equals, it's 200 for every bottle, 2,000 for every bottle. Bottle is X, right? So 2,000X plus 1,000Y. Now, why is this? It's because our profit, let's say if I make 10 bottles and 3 strips, well, I'm going to have 10 times 2,000 plus 3 times 1,000. Everyone happy how this equation has come to be? Perfect. Okay, now we have to identify the constraints. Now, so this is where we know, as we know, highlighters are your best friend. Let's have a look at the milling. We have 2 hours mill for X, 3 hours mill for Y, and the mill machine can only run for 80 hours per week. okay? So that means 2x, because remember our bottles are x, plus 3y has to be less than or equal to 80, because we can't have it being greater than 80, because the milling machine only works for 80 hours per week. So then, the next thing we look at is there's polishing to be happening. 3 hours to polish X, 1 hour to polish Y, and Mr. Blackett, he can only polish for 60 hours a week. How he does that and teaches, I honestly do not know. So that means we're going to have 3x plus y has to be less than or equal to 60, because 60 is the maximum time for polishing. Okay? Now, the most important constraint. You might find it obvious because we're human, but you know when we put this into a program, because this is linear programming, okay? We are going to be solving this manually, but it is going to be put into a computer. We need to let the computer know that x has to be greater than or equal to 0 and y has to be greater than or equal to 0, or else it will try and find a solution to the problem which may include negatives. Now, this is how we have formulated a problem, because this is going to help us to solve exactly what's happening. Could you imagine if I said this to you, okay, how would you even try and work this out? If I told you, this is how much everything takes, how would you even try and work this out without formulating the problem? Yeah, we would try and do this by trial and error, just keep going until we thought, oh, this is a good solution. What we're actually going to try and find is the optimal solution. This allows us to find the optimal solution. Now, all we're doing today is formulating the problem. This is all we're doing today, is we're going to read a paragraph, formulate the problem. That's all we're going to do today. Next lesson, we're going to look at what we then do once we formulate the problem. We're going to be graphing the problem, okay? Then after that, we're going to be solving the problem by using the graph. And we're going to look at, there's a few different methods to find the optimal solution, because we will find some good solutions, but we need to find the optimal solution, okay? Right, here we have a trickier example, okay? Now, everyone, we're going to pause the video. You pause it too. Let's read it. Okay, so as you can see, I have no idea really what's going on here. So sometimes it's a good idea to put this into a table, okay? Okay, so let's go. So a manufacturer supplies specialist stainless steels, 2 types of steel. Right, steel A has how much percent iron? 82%. 17% chromium, 1% carbon monoxide. The maximum is 15,000 kilograms. And the cost is £1.20. Can you see how I've put that in a nice table? Yeah. The second one, we've got 88%, 11.5%, 0.5%. There's 10,000 available, and it's going to cost £1. Required, right, so a customer wants 20,000 kilograms of stainless steel. Okay, so this is what they want. They want 20,000, right, their maximum. No more than 85% iron. So what does that mean? It means that, yeah, we want less than or equal to 85% iron, yeah? No more than 15% chromium. More than 15% chromium. Okay, so more than 15% chrome. No more than 0.9%. So less than or equal to 0.9%. Perfect. Okay, the manufacturer will allow type A with type B to produce the steel for the customer. So this is what they want to do. We did it. We've put it in a nice table so it makes sense. So now we can start to formulate the problem. So here we go. Define the decision variable. Step 1 is decision. Decision is let x equal type A, let y equal type B. Brilliant. State the objective. Do we want to maximize or minimize? Minimize. So minimize. Okay, now remember this is our costing here. It's whatever we're minimizing or maximizing, it's normally got to do with money. Okay, so we're going to minimize. So we can write P again. P equals 1.2x plus y. Okay? Yeah? Now, normally we say P is for profit. What are we trying to do? We're looking at the cost, aren't we? So sometimes you might see that people say C equals 1.2x plus y. Okay, because of the cost. To be honest, as long as you stipulate what P means, you can just write P equals cost, whatever's easier for you. Right, now we've got to state and simplify the constraints. Now, because of these are in percentages, I would convert them to decimals. Okay, so what do we have? This is really, really simple. So for the first one, what is this? 0.82x plus 0.88y has to be less than or equal to 0.85. Is that completely true?
Can't you just say iron has to be less than or equal to 0.85?
What is a little bit wrong with my statement? Do we remember what it said here? No more than 85% iron. So this is no more than 85% of x plus y. Yeah, because the iron's of x plus y. So we are going to have to expand and simplify. We're going to have 0.82x plus 0.88y. So less than or equal to 0.85x plus 0.85y. Now, okay, I'm going to take away 8.2x from both sides and 8.5y from both sides. I'm going to 0.03y is less than or equal to 0.03x. Y is less than or equal to x. Okay, so there is our first constraint. Just to be clear, this is one constraint and I've just simplified it. Why have I simplified it? Because I have an x variable and a y variable on both sides of the inequality sign. And if I'm going to be drawing a straight line, what would I do? I would simplify it and put it in the form y equals mx plus c. Okay? This is one constraint. We've just done the iron. Okay, the next one. I'm going in green. Okay, so very similar for this one. We're going to have 0.17x plus 11.5. Oh, not 11.5. That's silly. 0.115y has to be greater than 0.15. Lots of x plus y. Because that's how much of the chromium. Yeah? So, still on this one, expand and simplify. I'm going to have 0.02x is greater than... What's 15 take away 11.5? 3.5? Yeah. 0.035y. Okay, so Yeah, we can divide them by a number. So let's divide by 0.035. What's 0.02? 4/7, okay. So 4/7x is greater than y. And then that would be easy for me to draw, yeah? Because then I've got it in the form. So I could even say y is less than 4/7x. Now 4/7, as we know, is not a very nice decimal, so I'm just going to keep it to 4/7. Okay. Everyone happy with the second constraint? Perfect. Next one. Let's not go for yellow. Purple. Okay, carbon. Okay, so this one should be nice and easy. So 0.01x plus 0.005y is less than or equal to 0.9 lots of x plus y, because again that's the total. So we're gonna have, I've gone wrong. Yep. 0.009. Sorry guys, my fault. Okay, so then let's see. 0.009. So am I going to have 0.001x is less than or equal to 0.004y? Okay. So that means that y is going to be greater than or equal to 1/4 x. Because it's 1/4, isn't it? Yeah. Both the same amount. Perfect. Right. Then we have to look at this one. Okay. So different colour. Yellow. Orange. Okay. So now we know that 15,000x plus 10,000y has to be, it's required, it's 20, isn't it? Okay. So really we want it to equal 20. We don't want it less than, so what we do write is greater than or equal to 20. Okay, we know it's going to be equal to. We're just going to have this region to help us, okay? Because if we say less than, we want to make sure that we never want less than, we want at least 20,000, don't we? So that's why we put greater than. Now we also have to then think about, now this is where logic comes into play. Do we agree that x and y have to be greater than or equal to 0? Because we can't have any negatives, yeah? So x has to be greater than or equal to 0, y has to be greater than or equal to 0, because we can't make a negative number of type A. The other thing, is there any constraints? What's the maximum amount we can make for x? 15, we have to write that down. Okay, remember this is a computer that you're talking to. You need to write down every little thing. And the maximum we can make for y is 10,000, because this is different to this. This is saying both together has to be at least 20. This is saying we only have up to 15,000 of x. Okay, remember, if we're putting this into a computer program, you need to put in every single detail. So I'm going to highlight what you have to write. So we've got our minimizing our cost. Okay, we've got our decision variables. So we've got our first, y is less than or equal to x, okay? The second, y is less than 4/7x. The third constraint, y is greater than or equal to 1/4 x. Then we have our constraint here, okay? Now these are our variables. X has to be greater than or equal to 0. Y has to be greater than or equal to 0. It's told us we can only make up to 15,000 of type A, which is X, and the same for Y. So this is what we should be writing down to get the full marks. Here is a typical 5-mark question on formulating the problem. 5 mark is 5 minutes, off you go. Okay, so first of all, we need to make sure we read the question through first. Now, I've already read the question. And it says X palms and Y confiners. Okay, so it's already said what it is. For good practice, though, we are going to write let X equal palms, Y equal confiners. Okay, now I'm going to work my way through. So he has to plant at least 10 but no more than 80 palms. Okay, if that's at least 10 but no more than 80, that is going to be X has to be at least 10 but no more than 80. Okay? The next one, he has to plant at least 5 but no more than 40. So for Y, we're going to have to be at least 5 but no more than 40. He cannot plant more than 100 trees in total. So that tells me that X plus Y has to be less than or equal to 100. Okay, next one. Each palm needs 20 litres of water each day. Each confiner needs 60 litres and there's a maximum of 300 litres each day. So that must mean 20x plus 60y has to be less than or equal to 3,000. Now, everyone's happy with that? Then, I'm running out of colours, everyone. Yellow. Then it says, Ernest makes a profit of £2 on each palm and £1 on each conifer. He wishes to maximise profit. So, maximise P equals 2x plus y. Now, there's something missing from my sheet. Absolutely, we need to say that X and Y are both greater than or equal to 0. There is the 5 marks. Okay. Nice and easy. To make sure, I know some of you putting our hands up, some people miss some things. Please make sure you have read every single line. And if there's nothing to highlight on that line, wonder what it's doing there. Okay? There must be something. Okay? Right, graphical methods. So this is the second part now. Now this is my favourite part really, because what we're going to be looking at is the region that satisfies all the constraints. So in the IGCSE we would be shading regions, wouldn't we? Okay? So, I have no idea what any of this says. I'm not going to read it out to you. Something about a vase, but just pause this and read it at your own leisure. Okay? Right then, so let's actually get started at graphing the problem. So last time we were looking at formulating the problem. Now we're going to look at graphing the problem. Then we're going to look at finding the optimal solution in the feasible region. And then we're going to bring it all together. But we're splitting it all up into parts. Okay, so do you remember about Mr. Blackett was thinking about making these different types of bottles, and what we did was we added in our constraints. Now remember we had to get the non-negativity ones, yeah? The X and Y, and we had to set what we're maximising that. So now what we have to do, step 1, what are we going to do? We're going to start by plotting these. Okay, so let's just start by plotting these. Okay, so here we go. First of all, 2x plus 3y is less than or equal to 80. So if we wanted to, we could write this, rearrange this, and write this in the form, we're going to get y equals negative 2 over 3x plus 80 over 3. Okay, I could do this. I'm looking at this, I'm already thinking, God, this is messy. I'm dealing with thirds. Yeah, I'm just not going to do it, okay? So what I am going to do instead is, do you remember, I don't know if anyone remembers this. Oh, let me change my lightsaber. Do you remember you'd say, right, when x is 0, and you put your hand there. Can everyone see my hand? It's a tiny hand. When x is 0, 3y equals 80, so y equals 80 over 3. So there's our first coordinate. When x is 0, y equals... Oh, I've drawn my 8. It fell over. 80 over 3. And then now again, when y is 0, x equals 40. Because 2x equals 80, x equals 40. 40, 0. So that's the first coordinates, okay? Now let's get some colours involved here. Right, so we highlight... Oh, different colour, guys. We highlight this one. These are our 2 coordinates. So we're going to plot them on the graph. 0, what is 80 divided by 3? Right, 0, 80 over 3 is roughly here, 27 point something. 40, 0 is here. Is everyone happy with these coordinates? And everyone knows it's x before y, right? Okay, great. Now, the most important thing we need, did anyone know? A ruler. Why do we need a ruler? To draw a straight line, absolutely. What is going on with this angle? Okay, so please make sure you have a ruler. Draw your straight line. Brilliant. Okay, so there's the first one done. Now let's do the next one. 3x plus y. Okay, so y equals 0, 3x equals 60, x equals 20. So when y is 0, x is 20. And then when x is 0, y equals 60. 0, 60. Okay, so there's our next. Okay, right, sorry guys, this video is going to be really jumpy. This is 20, 0, 0, 60. Okay, I'm just keeping everyone on their toes. Okay, so use a ruler. 60, 20. That looks about right, doesn't it? Draw a nice straight line. Perfect. So, now, we obviously know that x and y has to be greater than 0, okay? So, what I do have to do, though, is I haven't quite finished this because I need to shade what... Now, honestly, I think it's a lot easier if we shade what we do not want. Okay? Because it's just going to make our lives easier. So, if we shade what we don't want, then we're going to be able to see what we want. Okay? Let's just do that. So, for the first one, we're going to have a look. Okay, so 2x plus 3y is less than or equal to 80. Okay, so what do I want? I want the area under the red line. So what do I not want? Above. Perfect. Okay, so I don't want above it. Perfect. Anybody confused as to how I did that? Okay, so what we could do is to know if we want above or below the line. There are loads of tips and tricks, but mathematically speaking, let's pick this point. What's this point here? 10, 10. Okay, let's substitute this in here and see if this is true. 2 times 10 is 20. 3 times 10, 30. Is 30 less than or 20 plus 30 is 50. Is that less than or equal to 80? So we know we want that point, and that point is based below the line. Okay, you can always try and put a point in. The other way I see it is actually, if it's less than, we want below the line. If it's above than, we want above the line. It's a trick. But when in doubt, put coordinates in and work it out. Now, let's have a look at 3x plus y is less than or equal to 60. So now we're going to have the blue line. Again, I can pick a point, and we can pick the point 10, 10, or I know that I want below the line. Okay, when in doubt, pick a coordinate and work it out. So this means I do not want all of this bit, okay? Now, very important. The last thing is the negations, okay, the non-negativity. X and Y need to be greater than or equal to 0. So that means I don't want this part here. And I also do not want this part here. Yes, you do need to do that.
She's the teacher.
Yeah. Okay. You need to get your highlighters out. You need to make this as colourful as possible. So right now, we are left with... Okay, so now, can everyone see? We are left with this region. This is my optimal region. This is the region that I want. How we find the optimal solution we're going to look at next lesson. All I want to know is that we're happy, is that we just want this part here. Everyone's happy that this is the part we want? Yeah. Perfect. Okay, I'm going to get rid of that part. And we're going to keep it in white. Because you see like the red, see that's like here, you know. So everyone's happy. Right. It's really simple. Now it's your turn. This is the problem we did earlier with the iron. Do you remember how much iron, the percentage? This is what we did earlier. We're breaking each problem out. So now it's test your understanding. I'm going to give you 5 minutes. Just a quick one. Sorry, very good question there. We know that if it's less than or equal to, it's a solid line. What happens if it's just less than or more than? Yeah, it's a dotted line. Everyone knows that anyway. Yeah. If you didn't know that, just get out and come back in when you remember. Okay, off we go. Okay, so the first line, y equals x. Remember, forget about the inequality while we're drawing the line. Is everyone happy? The line y equals x is literally, you know, wherever y equals x, you can just plot them. When x is 10, what should y be? 10, absolutely. So for the first line, we should have perfect. Oh. There is my first line. Y equals x. Everyone should be happy with that line. Okay, the next line. X, green, I'm going to do this one. X is greater than 1.7, right, okay, I'm going to change that around. What is 1 divided by 1.75? 4 over 7. So y equals 4 over 7x?
Yes.
Yeah? So what does that essentially mean?
It means for each one it goes 4 over 7.
Yeah, for every 1 across it goes 4 over 7. I could also say for every 7 across we go up 4. Okay? 5, 6, 7, 1, 2, 3, 4. Okay, we know it crosses at the origin because there is no plus c. Well, there is, but it's 0. So 1, 2, 3, 4, 5, 6, 7, up. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Okay, those of you who need to work on drawing straight line graphs, it's okay. Okay. I'll give you some of my year 9 homework. Right then. Nice straight line. There we go. Okay, next one. I'm going to do it in red. A quarter x. So this is literally saying y equals a quarter x. So for every 4 across, we go up 1. And again, it crosses through the origin. 1, 2, 3, 4, up 1. 1, 2, 3, 4, up 1. By the way, this method, going across 4 and up 1, it only works, it works all the time, but make sure that if this is 5,000, this is 5,000. If this was 10,000 here, you go across 4 and up a half. or across 2 up 1. Yeah, it needs to be in, I don't know the word. 1, 2, 3, 4. And up 1. What does it need to be in? Yeah, proportion. Thank you. 2, 4, 1. 2, 4, 1. Brilliant. Okay, so the next line looks something like this.
But shouldn't the green line be dotted?
The green line should be dotted. It should. I was more panicked that you guys forgot how to draw lines. There we go. Look at this. We'll just add some dots in. Okay. So perfect. Brilliant. Right, the next one. X has to be less than or equal to 15,000. Okay, I'm going to have to, I think yellow is the number. No, it's purple. Okay. I'm going to do this one in purple. Where is X less than or equal to 15,000? It's this line here, right? The straight line.
Yeah.
Yeah. Nice, there we go. Okay, now we're going to use yellow. Okay, the next line is y is less than 10,000. Oops. 10,000 is here. Okay. There we go. My line is completely straight, by the way. The graph is wonky. Okay, x plus y is greater than or equal to 20,000. Remember when I say when x is 0, what is it? When y is 0, I'm going to go for orange on this one. Okay, so my coordinates here are actually going to be 0, 20,000, 20,000, 0. So it's this point and this point. I'm going to draw a straight line. Oh, sorry guys. Why is my angle not changed from 45 degrees? There we go. Okay. Oh. Okay. Now, lastly, we know about the x and y. So now I'm going to start shading. Okay. Are we ready? Guys, can I just ask you to be quiet because I'm trying to record this for you and all I can hear is noise. Okay, so first of all, is everyone happy with the x and y being positive? Yeah? Okay, so now y has to be less than x. Does anyone remember? Am I shading above or below the line? We want below the line, so I shade above the line, so the blue line. Okay, next we have the green line. X is greater than 1.75y. That technically means y is less than. So do I want above or below the line? I want below, I shade above. And again, put coordinates in if you need to. A quarter x is less than or equal to y. So this means y is greater than the first red line. Okay? So, do I want above or below the line? If it's greater than, I want above the line. So I'm going to shade below this line. Okay. Then x is less than 15,000. I want the left-hand side. So I'm going to shade the right-hand side. Okay? It says y is less than, so we want less than 10,000, so I'm going to shade above the line. Okay? Then, remember this part shaded too. Lastly, x plus y is greater than 27. I want above the line, so I'm going to shade below the line. Okay, so very carefully, guys. Here is the area that I want. I'm going to have this dotted line, solid, solid, Okay, that is the area I want. Essentially, this is our optimal region. Okay? Right, we're going to do 3 different things. If you need help drawing, Dr. Frost. If you need help shading, I've got something else. And if you're happy, move on to the next one. So, Dinah is to have a rectangular swimming pool at his villa. He wants the width to be at least 2 meters and its length to be at least 5 meters. He wants its length to be at least twice its width. He wants its length to be no more than 3 times its width. Each metre of the width of the pool costs £1,000 and each metre of the length of the pool costs £500. He has £9,000 available. Let the width of the pool be X metres and the length of the pool be Y metres. Show that one of the constraints is this and find 4 further inequalities. Okay, that's worth 4 marks and we've been given a lot of information. Okay, so did I already read the whole question? Yeah, I did, didn't I? Okay, right, so let's think about what's going on here. Now, we know it already said about our X and Y. So width is X, length is Y. Now, just to make my life easier. Okay, so width is X. Okay. At least twice its width, 3 times its width. Width 1,000. Okay, brilliant. Okay, I'm going to have to write this. Do you remember I did a disclaimer the other day? Length 500 and there seems to be 900 available. Okay, perfect. So, I know it says A and B, but I'm going to ignore what A and B says. I'm just going to go through the whole thing and hope that one of them comes, and then I've done B anyway. So he wants its width to be at least 2 meters. So what does that mean? That means that X has to be greater than or equal to 2, right? And its length to be at least 5 meters. So Y has to be greater than or equal to 5. Right, it wants its length to be twice its width. Okay. So let's just try this. So it wants its length to be at least twice its width. Length is Y. So this has to be at least twice. Okay. I don't know if I'm right yet. Let's put some numbers in. If the length is 1, it wants the length to be at least twice its width. The width needs to be minimum 0.5, right? I get confused. This is why I'm going through the numbers. So let's think about it. He wants his length to be at least twice its width. Yes, if my width is 0.5, this has to be 1. 1 is greater than or equal to 2 lots of 0.5. Yes. Okay, that one's fine. It wants its length to be no more than 3 times its width. So if this is 1, what do we know? Length to be no more than 3 times its width. Wait there, guys. I'm struggling. He wants his length to be no more than 3 times its width. Okay, I think I need to make this a 1. Let's say the width is 1, 3 times is 3. Y is less than or equal to 3s. He wants its length, so Y has to be less than or equal to 3 times, yes. Yes, is this right? Okay, now remember this is the part I struggle with, so that's okay. Right, then what do we have? Each metre of width is 1,000. So 1,000x plus 500 Y has to be less than or equal to, it only has 9,000 available, right? Yeah? Yes. Perfect. So that means that, so we can simplify this. Can everyone see, first of all, I could divide everything by 100. So I'm going to have, yeah, I could divide everything by 500. Let's just, I don't want to do that yet. Okay, now I'm going to divide everything by 5. 2x plus y is less than or equal to 18. Yeah, okay. Everyone happy? I have all my constraints. Yeah? Brilliant. Okay, next question.
X is greater than or equal to 2.
What do I do now? Draw my graph, right? So, someone's going to have to tell me what the equations... Wait there. X is greater than or equal to 2. So let's just quickly... Okay, x is greater than or equal to 2. Here?
Yeah.
Did you say greater than or equal to?
Yeah.
So we want above it. Where am I going to shade? Well, we don't want. Okay, what was the next one?
Y is greater than or equal to 5.
Y is greater than or equal to 5? Okay. So I want above it, so where am I going to shade? Below it. Okay, what's the next one?
Y is greater than or equal to 2x.
Y is greater than or equal to 2x. Okay, guys, watch this. Can you see how my axes is not in proportion?
Yeah.
So y equals 2x. Okay, so this means that crosses here. For every 2 across, how many do I go up? 1. Look, for every 2 across, I go up 1. Every 2 across, I go up 1. 2 across, I go up 1. I need to use the scale.
For every 1 across, 2 up.
Yes, well, why didn't you tell me that? 1 across, 2 up. See, look what happens when I trick you. Oh. 1 across, 2 up. 1 across, 2 up. 1 across, 2 up. Okay, can everyone see why we have to make sure that we know exactly what's going on? Perfect. So then we're going to draw our straight line. Now, what was it? Was it y is less than or greater than?
Greater than.
Okay, y is greater than. Now,
Or equal to.
after speaking to a few of you, we had a trick. Now, the trick was, if the y is on the left-hand side, okay, it needs to be on the left-hand side and it needs to be positive for this trick to work. And this is why we don't use tricks, because tricks only work for certain circumstances. This trick only works if y is on the left side of the inequality and it's positive. If it's less than, where do we want? Below the line. If it's more than, we want above the line. Did you say this was greater than or equal to? Okay, so I want above the line. Where do I shade? Below the line. Perfect. Next inequality. Y, is it 3x?
Yeah, y is less than or equal to.
Y is less than or equal to 3x. So for every 1 across, I'm going to go up 3. 1 across, up 3. 1 across, up 1, 2, 3. 1 across, up 3. Okay, again, it's going to cross at the origin. Okay, there we go. Now it says less than. I want below the line, I'm going to shade above the line. Oh, I thought that ruler would have stopped the shading. It doesn't. Okay, next one, what was it? 2x plus y equals 18 or something?
2x plus y is less than or equal to 18.
Okay, 2x plus y is less than or equal to 18. Now, first of all, if I let x equal 0, y equals 18. If I let y equal 0, x equals 9. 9, 0, 0, 15, 16, 17, 18, yeah? Perfect. Okay, it says less than. I want below the line. I'm going to shade above the line. Okay, perfect. I'm now going to hide this ruler because it's annoying. Okay, so you can see, I'm going to highlight in yellow what we actually want. I can label it art. Can everyone see? I want this shape here. It's kind of like a 1, 2, 3, 4. It's a 5-sided shape. A trapezium's not 5 sides.
It looks like a trapezium.
It looks nothing like a trapezium. There's an extra side. Okay, so this is how we shade it. Right, some of you have got extra worksheets to do some extra shading. Everyone's happy, and we know that we need to practice this. We're going to do some exercises. Well done. So now what we're going to do is we're going to actually start by finding the optimal point. Okay? What we know, this is a graph that we did earlier, by the way, everyone. Okay, in the examples, we shaded this, we formulated this problem. This is still the problem about, you know, the stainless steel.
Yeah.
Okay, we're just getting each one. Here is our optimal solution. Okay, now it's a good job I have a ruler. Okay, because we're going to see the sliding ruler method. Now, the sliding ruler method is a bit difficult. Okay, and I think when I record it, we'll show this ruler, won't it? I mean, if not, we'll find out. So, how do we use this ruler? How does it work? Okay? Someone's been doing some pre-reading. Well done. We're going to use the line of, you know, the maximise or minimise. Yeah, that's going to help us know which way, because the sliding ruler method is basically this. Let's say we're here. We're going to keep sliding, okay, until we find the first point. What's the first point I reach? It's this top of the triangle here, wasn't it? Did everyone see that? Yeah. It was the top of the triangle. But imagine if my ruler looked like this, and I kept it at 25 degrees, and I did the sliding ruler method. Which one would it touch first? Yeah, it would touch this bit, wouldn't it? Yeah. Okay? So, is it important at what angle our ruler is if we're going to use the sliding ruler method? Yes. 100%. How do we find that angle? Well, for those of you who are on the YouTube channel, type in that Desmos link. Everyone else, we're just going to look on my laptop. So after watching the Desmos slider, we have a bit more of an idea. Right, we're going to move on. So, what on earth? Let's just get rid of the ruler for a second. We'll come back to it. So, we can plot the objective function as a line. Okay? For example, let's let C equal 6,000. If we let C equal 6,000, here we have our line. Yeah? Okay? No matter what C equals, if we did C equals 10,000, we're still going to get the same gradient. Yes, the gradient's still going to be the same. Okay? So, using our ruler, now this is, I don't know why, it's just, it is pretty tricky, and this is why we've got some people with common sense. Imagine trying to keep your ruler at this angle the whole time. Okay, what angle is this roughly? It's about 50 degrees, isn't it? Yeah? It's not 50 degrees if we were to measure from, it's just reset itself. I don't know why the ruler says it's 50 degrees. Because it's measuring from the other side, right? So, what do? We go, keep it at 50. Boom. This is the first one. Okay, it's the first one here. This is going to give us our minimum point using this slider. Okay? Okay, so remember, you can then try a few different values of C. This is showing the ruler method. I'm going to show you the next one. So we can see on here, what we've done is we used 6,000. We realised that when we got 6,000, we were here. This is nowhere near our objective line. So what would I do then? I'd double it. I'd maybe try 12,000. Yeah? you want to keep, with the ruler method, you have to keep showing that you're getting closer and closer. Okay, ideally you want this point in here. Okay, now, what you will notice is every time we put something in, of course these are all going to be parallel because they have the same gradient. Okay? And we're going to intersect the feasible region here, aren't we? Now we can find this coordinate. How do we find this coordinate? We know we're not going to do guessing, okay? You're not in year 11. We're not going to read the graph and guess. We know this coordinate is when these two lines intersect. So what do you think we're going to use? Simultaneous equations. We know that the dotted line is the line x equals 1.75y, and we know that the other line is x plus y equals 20,000. I'm going to solve using simultaneous equations, okay? And then I'm going to find a coordinate for x and a coordinate for y. If I substitute in, that will probably be the biggest thing, won't it? So I'm going to have, if I substitute this in, I'm going to have 2.75y equals 20,000. So y equals 20,000 divided by 2.75. Okay, what does x equal? X is going to equal 1.75 lots of 20,000 divided by 2.75. Okay, now someone with a calculator is going to give me the answers for x and y. Okay, so x is 140,000 divided by 11, and y is 80,000 divided by 11. Now once we find out x and y, we're going to substitute this into our maximisation or minimisation, yeah? Okay, so remember, we're going to substitute this into C to find out the cost. 1.2 lots of 140,000 over 11 plus 80,000 over 11. Now, as you can see here, I know these are going to be decimals, but I know they're divided by 11. They're not going to be very nice. I'm going to keep everything exact until the last moment. Okay, I'm going to put this into my calculator, and I'm going to get C equals 248,000 divided by 11. Now, I can't keep the cost like this, and I definitely know with cost that cost is rounded to how many decimal places? 2, or sometimes the question will say to the nearest pound. Okay, so if we do this one to the nearest pound, I'm going to get 22,545. So that is the final answer of the cost using the ruler method. Okay. So for finding a maximum point, the maximum we're looking for the last point. The minimum we're looking for the first point. Yeah? Okay? So, here is a formulation. Step 1, solve it. Step 2, plot it. Step 3, shade it. Step 4, get your ruler method. Off we go. Okay, so pause it now and then I'll show you the answer. Okay, so here is the answer now. And then the objective function is to maximise. Did anyone do this question actually? So the answer is when P equals 36, we have our x coordinate of 6.75, our y coordinate of 4.5, and that gives us maximum profit. That's this one here. Now, as you can see from this, you have to use simultaneous equations to find the exact coordinates, and when you've done your ruler method, it should, it goes like it's 10 and 4, so that'd be like your first straight line. Then the next one is 6 and 15, That'll be your next straight line, and then the next one, blah, blah, blah. Okay, so you'll be able to see what's going on. But once you do the 6 and 15 one, you can see that the only optimal point left is this one, and this is the last one, so you know you don't have to draw 2 lines with the ruler. Okay, well done. Okay, so test your understanding. So the first one I'm going to do in blue. I've got 8x plus 3y is less than or equal to 480. So remember, when y is 0, 8x equals 480, so x equals 60. Okay, so when y is 0, x equals 60. And then when x is 0, 3y equals 480, so y equals 160. So here's my first graph. Line, thank you. Okay, so my first line is here. Okay, and I'm going to draw a nice straight line. Beautiful. Okay, my second line. 8x plus 7y is greater than or equal to 560. So if we let y equal 0, 8x is 560, so x equals 70. Okay, and then if I cover y, if x is 0, 7y is 560, so y is 80. So, here's my second line. Okay. Remember we need to use a ruler. It's really important. Okay, perfect. Then we have a look at the next line is y is greater than 4x. So we know it crosses here. This means for every 1 along I go across 40. So it's like for every 1 along I go across 4. It's the same, every 10 along I can go across 40. 10 along across 40. 10 along across 40. Remember, you have to make sure that you use the scale that you have. Okay, you only need 2 dots to draw a straight line, but some of you in the classroom really struggle with 2 dots, so just do a few more, okay? Right, there we go. So, and then obviously, it says, so now we're going to start shading in the parts we don't want. X and y has to be greater than 0, so we can shade this part, but we can see we actually don't have this part of the graph, okay? But it's just good to shade it just for old time's sake. Then for the blue line, it's less than, okay? So we want this part here. Where are we going to shade? Above, yeah, the part we don't want, just to make our life easier, okay? Now, some of you might always shade the part you want. That's fine. I just find it got a bit messy and you don't really know which part you've got. So as long as you're consistent, if you always shade the part you don't want or always shade the part you want. Then for this one, we want above the line. So where do we shade? Below the line, because we shade the part we don't want. There we go. And then for y is greater than 4x, we want above the line, so where do we shade? Below the line. Okay, so can everyone see our optimal region now? Okay, and we can even, okay, label it with an R if we wanted. Now, even though this is great to label it with R, I would suggest we do not label it with an R, just because as long as, like here I struggle to see the coordinates. So yeah, so just, you know that's your optimal region in there. Okay, now it says the objective function. So now it says the objective function f equals 3x plus y. Making your method clear, determine the minimum value of the function and the coordinates of the optimal point, the maximum value of the function and the coordinates of the optimal point. Now we can see in this question it's saying making your method clear. At the minute we've just used the ruler method, haven't we? Okay, there is another method. So for this one we're just going to use the ruler method, and we know that we could take y equals minus 3x. Yeah? So, and then what we can do, this is how we show the ruler method. So we're going to do y equals minus 3x, let's plus 10. So if I was to draw this line, minus 3x plus 10, or we could just have 3x plus y equals 10. Now, when I'm drawing this line, tell me, do you think it's a good idea for me to do 10 divided by 3? No. So what do you think I'm going to make for 10? Yeah, I'm going to make it a multiple. Remember, guys, you choose what you're going to put in here. Be sensible. Okay, use your common sense. I know you have it. So, let x equal 0, y equals 30. Okay? Then, when y equals 0, x equals 10. So, you can see here, this is my first line for the ruler method, isn't it? Now, what we have to do... Now, luckily here... I can set this. So can you see I've set my angle at 56 degrees? Now for me on this iPad, it's really lucky because what I can do now is I can just keep going across. This is the first point. Can everyone see this first point on the left? What point is this? 0.80. So this means my minimum value is 0.80 because this is my first point. Yeah? Now, let's say I did not have this ruler. None of you have an iPad in the exam, do you? No, because you're not allowed electronics. So of course you don't have this ruler that magically stays there. What you would then do is you would then keep doing, okay, that's 30x plus y equals, what's the next multiple of 30? 60, okay? So if you were to do that, you know, x is going to equal 20 when y equals 60. Okay, and then we're going to draw our next line here. This is what... sorry, for some reason... There we go. I'll try and draw. So this would then be our next line. So you know how you guys were saying, how am I going to show I'm using the ruler method? This is how you show it. You just keep drawing lines. Okay, then you'll see a pattern. Okay, it's clearly going up in 10. So the next one is 30. And then this one is going to be 90. I want to say it's somewhere there. It will tell me. Okay, so you can see here, because we're using the same gradient, the first one we've crossed is this one. This is how you show it using the ruler method. Okay, so my first one is 0.80. Now let's say I kept going. Okay, kept going. Oh, can you see? Who would have put bets on it would have been that blue one at the top? I mean, I was close, but actually, if we look, which one does it go to last? Here, where it crosses, doesn't it? Now, here's a sensible question for you. Am I going to read off the map where this point is? No. What am I going to use? Yeah, simultaneous equations, simultaneous equations. I don't know. They could be anyway. That's what we're going to do. So which line? Yellow and blue. So to find that coordinate, which is going to be our maximum value, we are going to solve. Let's do it in purple. So we're going to solve ax plus 3y equals 480. And y equals 4x. So this is really nice. We can just substitute. We're going to get 8x plus 12x equals 480. 20x equals 480. That means x equals 240. 24. Yeah, that looks about right. How do I find y? 4 times 24. 20, 40, 60, 80, 96. So here, my maximum coordinate is going to be 24, 96. And this would mean, for example, if x was jumpers, y was shorts. So to minimise profit, I wouldn't make any jumpers, I'd make 80 shorts. To maximise profit, I'd make 24 jumpers, 96 shorts. Does that make sense? Yeah? I know what you're thinking. It doesn't say shorts anywhere in the question. You're right, I just made that up. So that is how we use this ruler method, okay? And then if you just keep we haven't done it for the maximum, but what you do is just keep going. Keep going in this, and then you'll finally see which one. You can see this is the first one, can't you? Then you'll see the second, the third. So let's just do this so we actually can see. It was 56 degrees. Okay, here we go. So the next one would be 40, and we were at 90. 90 plus 30 is 120, yeah? Okay. Then the next one would be 50 and 150. Okay. Then the next one would be 60 and 180. Okay, so actually, guys, can I just say this is really important to see, right? We can actually see that we've done the ruler method, and actually we can see that both this point and this point are in this quadrant, aren't they? Yeah? If that's the case, you are going to have to find out, you're going to have to go in between 50 and 60, do 55. Yeah? And then up here to see which one it is, okay? Everyone happy with that? Brilliant. So, then for the final question, it asks for the value of the function and the coordinates. We've written the, we didn't write the value. So f is going to be 3 lots of x is 0 plus y is 80 for the first one. And then for the second one, our f is 3 times 24 plus 96. 168. Okay, so there we have it. So that is how we've done that question. Okay. Brilliant. So the vertex testing method, okay, I want to run through this really quick. So if you're struggling to keep up with the first part, you need to go away and do some work on your own. The second part, where we actually talk about the vertex testing, of course I will slow down and teach you, but the first part we should all be relatively happy with, okay? First of all, you have to draw the graph. It's simple. Okay, 2x plus 4y is greater than or equal to 30. So I've got when y is 0, x is 15. And when x is 0, y is 7.5. Everyone happy with that? Okay? If you're not, what do you think you have to do? Yeah, go away and learn it. Okay, we can't spend any more time on learning how to draw y equals mx plus c. Okay? Done. Right, next graph is 3x plus y is 25. So when x is 0, y is 25. Okay, and then when y is 0, 25 divided by 3, it's like 8.3 recurrent. 7, 8, it's about there. Okay? So there is our next line. Okay, next one. We have x plus y is greater than 13, so I know 10, 11, 12, 13. 13. Okay, if you're finding this a little bit difficult, how fast I'm going with the graphs, this is something you need to work on. Okay, because I'm just going, we should be happy with this part now. I need to move on to the teaching. And then, let's get green out. Y is greater than or equal to 1. So that's wonky. That's there. And then x is greater than or equal to 0, which is the axis line. Okay, I'm going to shade what I don't want. 2x plus 4y is greater, so I want above, I shade below. So that's the red one, okay, guys? Okay, blue one. It's greater, I want above the line, I shade below. Okay, x plus y is greater, one above the line, I showed below. I showed below because I want above, and then I don't want any of that. Okay, boom. Everyone happy that my optimal region is this one here? Okay, so if you struggled with anywhere up to that point, this has got nothing to do with linear programming. That is just shading inequality regions. Yeah? Y equals mx plus c. That's all that is. Okay, now what we're going to look at is the vertex testing method. So sometimes, you've seen before, a lot of the time we've had enclosed shapes, haven't we? Yeah, I mean, a few days ago someone said it looked like a trapezium, even though it was a 5-sided shape. Okay, what do we call that? An irregular pentagon. Okay? So, sometimes we don't have the shapes that are enclosed. We have something like this. This is okay. What we are going to look at are the different vertices. So, as you can clearly see, we have one, because this is like coloured in, we have one here, 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 and here. Okay, can everyone see I have 4 vertices? Okay, the first one, I'm going to start at the top and work my way down. The first one is 0, 25. So I write down the vertices, I create my own table, I write down the coordinates, and then I substitute it in the optimization function. Whether it's minimize or maximize, it really doesn't matter. So I'm going to do 140 times 0 plus 170 times 25. I'm going to get 4,250. Okay? That's how I get this one. Right, part B. Now for part B, I can clearly see that it is on 6 and 7. Okay? If it was a bit hit and miss about, is it, like you can see, it crosses here at 6 and 7. If it was a bit hit and miss, you know, like earlier I said, you know, if you're really not sure, like I think one of the answers was like 24 divided by 3. Okay, if you're ever looking at thirds, how do you find the coordinates? Simultaneous equations. Okay? If it's easy to read off the graph, if it's exact, you use this. So again, we're going to do 140 times 6, because that's my x, plus 170 times 25, and we're going to get 2,030. Okay, then the next one, okay, is... Pardon? Oh, this is 7, isn't it? It looks like a 7. I think you guys are blind. Just really squint. Yeah, exactly. It is a 7. Okay. The next one, okay, do I really know what's happening here? No. Okay, so what's that, red and yellow? Yeah? Okay, I'm just going to quickly do simultaneous equations. When in doubt, work it out. Okay, I'm going to do 2x plus 4 lots of 13 minus y. Is everyone happy how quickly I've rearranged that? Yeah? Okay, if not, go back to pure 1. 2x plus 26, 52 minus... Wait a minute. That should be an x. Minus 4x minus 30 equals 0. So I'm going to get I'm going to get 2x equals 22, x equals 11. Perfect. If x equals 11, y equals 2. Okay, so I've just done simultaneous equations. Yeah? Slow down and do that on your own time. Okay? So then when I substitute this in, I'm going to get 1,880. Okay, and then for the last one, here, I'm not sure where it crosses. What am I going to do? Simultaneous equations. When I do the simultaneous equations, I get 13 and 1. I'm going to have 1,990 when I substitute in. Now, this is a minimize function. So what am I looking for? The minimum. And which one gives me the smallest? C. The smallest number is C, right? Yeah? So, to minimize the function is when x equals 11 and y equals 2. C will equal 1,880. So you can see this is slightly different than the ruler method because we're actually testing all the vertices. Okay? Okay, very quickly, test your understanding, and to make sure that you're happy, here is a graph that Mr. Blackett has already drawn for you. So it's really simple for you to find the coordinates. If you're not sure of a coordinate, what do? Simultaneous equations. Okay, off you go really quickly. Okay, so well done. Mr. Blackett has made a typo. This is x equals 3, as we can see from the inequalities, and you can see it's 3 here, okay? So thank you so much. So we do appreciate these PowerPoints. It makes life a lot easier. So here we have the x's, y's, and here we can see. Now it says minimize. So for our minimization, we will be using C, where x is 3 and y is 1. Perfect, well done. So now we've completely covered that. Okay, the last one. The last one is sometimes it will ask you for solutions with integer solutions. That's what it will ask you. Okay, so for example, when we look at this, how are we going to find the coordinates of the optimal point? Okay, it's going to be, this one is to maximize, isn't it? Now, if I just use the ruler method very clearly, I can tell that this one is going to be the furthest away. Okay, now when I look at this really closely, it's not very nice, is it? So what am I going to do? I'm going to use simultaneous equations. I've figured it out. Now, the optimal point is 14th and a 7th and 17th and a 7th. Okay, this is the coordinates of the optimal point. Now, when we are looking at, like, by the way, I've done this really quick. Like, you guys, imagine I've got the answer. This is the answer, yeah? You've done either the ruler method or you've done this method, and this is what we get. You solve simultaneous equations, and this is the optimal point, okay? Right, I'm just bringing it all together. Now, can I say to you, you need to make 14 and 1/7 of a jumper? No, don't be ridiculous, okay? It's foolish, okay? So, what we do is we imagine an integer box. So, where is 14 and 7? Okay, this is the box. This one is going to be 14, 17. This one, 15, 17, 15, 18, and 14, 18. Is everyone happy with how this looks? Yeah? Because this coordinate is somewhere in this box, isn't it? 14th and a 7th and 17th and a 7th is roughly here. So, what we have to do is we have to look on the next page to check the correct solution is going to be one of these 4. But one of these coordinates have to lie within the region we want. Now, you can sit there and draw a box out, okay, and test each one, as you'll see on the next page. It's really simple though. We can start, we will test a few, but we can start by cancelling the ones that are definitely not there. So here's the optimal region, okay? We can clearly see from this box, here's the region. Where is the nearest whole number? It's this one, isn't it? This is the edge of the box. Can we see that? So, here is the box where our optimal region lies. This is 14 and a 7th and 17th and a 7th. Yeah? This is where they cross. They cross in the box. Yeah? This coordinate is still 14, because it's 14 across, but now it's 18, isn't it? Because it was in between 17 and 18, 17 and a 7th. Yeah? This one is going to be 15, 18, isn't it? This one, 14, 15, 17, and this box is 14, 17. Which one, even though our optimal point is here, it is not, here is our optimal point. We're going to use this. Here is our optimal point. We need it to be an integer. So what's the closest integer to this optimal point? It's this one, because this is inside the region. Okay? Now, when in doubt, draw it out, or if we look on the next page, see that box? This is that integer box I was telling you about. See? It looks really tiny from there, doesn't it? If you're not sure, this is what you would do. On this page, we have our coordinates. You could substitute them in here. For example, let's pick, we know 14, 17 is going to work, okay? We know that's going to work anyway, so let's do 15, 17. 2 lots of 15 plus 3 lots of 17. And what we're checking is we're checking our constraints here. 2 lots of 15 plus 3 lots of 17, that actually equals 81. Is 81 less than or equal to 80? No. So straight away, this is not in the region. Okay, we can cross that out. Now, we were able to see that from the graph when we zoomed in, didn't we? Now, did you see how far I had to zoom in for that? Yeah? Unless you've got supersonic vision, like Superman. Sometimes we have to do this where we try things in, okay? And then what we find is when we put in 14, 18, we get 82, and we get 84. There's no need to attempt these ones if this one is already failed. So we know that all of these are not in, so we just focus on the first one. Okay, so the first one will be our answer, because it's asked for an optimal solution with integer solutions. Okay? So our x and y has to be an integer. So, now we have finished linear programming completely. Done. We've looked at all the different methods. Everyone's got a huge pack of exam-style questions of linear programming. That is what we're going to be working on. Okay? Well done.